Objective 3 in 7.3 is probably one of the most important things that you're going to learn this chapter. It's sort of the thing that's going to be carried through other courses that you take because it's the process of simplifying radicals. We simplify expressions, we simplify fractions, we simplify radicals as well. So the first thing is identifying that a radical is not factored, not simplified. And so the first thing you want to check is your radicand. So if you remember that the radicand is the number that's under the square root sign or the radical sign, you want to make sure that there aren't any factors of the number or the variable that's underneath the square root sign that could be factored, and one of the factors could have a square root. And that's not going to be a lot until we do the process, but just know that you're going to be looking for factors that you can take the square root of. You're going to want to make sure that your radicand is not a fraction, and you're going to want to make sure that even if your radicand is not, like the whole thing's not a fraction, that your denominator can't have a radical in it. And then lastly, you're checking that your variable, that the exponent on the variable is not greater than your index, because that'll be a sign that your radical is not simplified. So how do we simplify? Well, the steps to simplifying radicals are looking to see if your radicand has any perfect square factors. So for example, if I look at the factors of 20, I've got 1 and 20, 2 and 10, and 4 and 5. 4 is a factor of 20 that I can take the square root of. So what we're going to do is the reverse of multiplying. So we are going to break our radical up into factors. So they're going to be multiplying radicals. And the first radical is going to contain your perfect squares. And then the second radical is going to contain the things that you can't take the square root of. So if we have the two factors of 20 being 4 and 5, 4 we can take the square root of, and 5 we can't. Then you look at your variable. The index here is a 2. Since the 3 is greater than a 2, then you know that it's not simplified. So what you're going to do is look for a factor of x cubed that the exponent is divisible by 2. So for example, x cubed could be broken up into x squared and x. Being divisible by 2 is how you're going to determine if it's a perfect square. So x squared is a perfect square and x is not. And so the x squared will go under the first radical sign and the x will go in the leftover. And so step 2 is write the number under the radical signs of the perfect square first. Step 3, you're now going to take the square root of that perfect square, and then you're going to make sure you can't go any further. So 2x times the square root of 5x. 5 doesn't have any perfect square factors, and x, the exponent, is 1, which is now less than the index. So you're good to go. So let's try a couple. So we're going to look at the square root of 18. So the first thing I do is I split the radical up into 2. So the first radical is going to contain my perfect squares, and the second radical is going to contain what's left over. So I'm looking at my factors of 18. I've got 1 and 18. You're never going to choose this because you're not going to put a 1 in the first radical. So I'm going to go on to 2 and 9. Now 2 is not a perfect square, but 9 is. So I'm going to put 9 under the first radical sign and 2 into the leftover. Then I'm going to take the the square root of 9 to get 3, and I'm left with 3 times the square root of 2. Now again, all we've done is like we do with a fraction. So 4/6 is the same as 2/3, just like the square root of 18 is the same as 3 times the square root of 2. So we're just writing our expression in a different form, a simplified form. So if you plug into your calculator the square root of 18, and you plug into your calculator 3 times the square root of 2, you'll get the same irrational answer. So it's a good way to check that what you've done is correct. So I want you to pause the video right now and try the square root of 72, and I want you to do it for a reason. So please pause the video and come back when you're done. So looking at the square root of 72, now I like to write my factors. So I'm not going to do 1 and 72, but I'm going to go to 2 and 36. So if you did it this way, then you'll find that the first radical would contain 36 and the second radical would contain 2. The square root of 36 is 6 times the square root of 2. But maybe instead of writing out your factors and starting by dividing by 2 and then dividing by 3, maybe instead you're trying to do it in your head and you think, oh, 72 is 9 times 8. So I could simplify the square root of 72 into the square root of 9, because that's a perfect square, times the square root of 8. take the square root of 9 and get 3, and 3 root 8. And if I plug this into my calculator, 3 times the square root of 8, I'll get the same as the square root of 72. But you wouldn't get full marks for simplifying. Why? Because 8 still has a perfect square factor. If I was going to factor that radical further, 8 is the same as 4 times 2. Now keep in mind these are all multiplying together. So this is 3 times the square root of 4 times the square root of 2. So that when I take the square root of 4, this is 3 times, oops, sorry, I wrote 3 twice. 3 times 2 times the square root of 2. So 3 times 2 is 6 times the square root of 2. So it didn't matter that I did this step first, as long as you recognize that the square root of 8 still has perfect square factors. So it's just like if I had the fraction, I don't know, 8 over, am I going to pick a good one here? 8 divided by 4, 8 over 16. Right? And let's say I simplified it first to, I said 2 goes into both, so I'd say 4 over 8. And then I noticed that I just had to simplify further. So maybe I noticed 2 goes in again. Maybe I notice that 2 goes in again, right? It doesn't matter how many steps it takes you to simplify, as long as your final answer is fully simplified. So now I want to show you what happens when you have a huge radical, like 240. I don't want to start listing all of the factors. I don't want to do 1 and then 2 and then 3 and then 4. I mean, it might work, but it's going to take you a while. So instead, what I do is you might have your multiplication sheet in your formula package. In your first course package, you had a formula sheet, and in there, I think, if I remember correctly, I threw in a multiplication table. And if you look at the diagonal in the multiplication table, it's got 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 25, 36, 49, 64, 81, 100, 121, 144, 169, 196, and so on and so forth. So you've got this list of all the perfect squares. And so instead of finding the factors of 240, you can actually use this list to find the highest perfect square that goes into 240. So don't start at the bottom of the list, because then you're not finding the highest perfect square. You want to prevent yourself from having to simplify twice. So I'm going to start at whatever's closest to half of 240. So half of 240 is 120. So I'm not going to choose 121. I'm going to choose 100. Now I know 240 is not divisible by 100, so I'm going to try the next one. So I'm going to go 240 divided by 81. Nope. So I'm going to go 240 divided by 64. Nope. I'm going to go 240 divided by 49. I'm going to go 240 divided by 36. 240 divided by 25. 240 divided by 16. And there we go. So if I did it using my calculator, I found that 240 is 16 times 15. And then I take the perfect square of 16, which is 4, and I'm left with 4 times the square root of 15. So that's one way to do it. Another way to do it is the other way. You know, you could say, oh, hey, I know 4 goes in. So 240 divided by 4 is 60. So I could go, okay, this is root 4 root 60, which would be 2 root 60. And then I could simplify root 60. Maybe I notice that 4 goes in again. And I'm left with root 4, root 15, and then this would be 2 times root 15, and I get 4 times root 15. So, you know, however it is, but you want to make sure that you're finding the highest perfect square. There's another method as well. If you're coming from Math 49 and you did factor trees, you could break 18 up into its prime factors. And then you're looking for pairs. So for example, if I look at 18, it's 3 squared times 2. So then I know that this would be 3 root 2. So there's more than one way to do this. If you want to find more ways, feel free to find other videos. If you want me to go into more detail about the factor tree method, I'm more than happy to do it. So maybe we'll do one more that way. So if you are into factoring trees, you know, 2 and 36, right there I would stop though. I just find this kind of slower, but some people like it. 2 times 9, 2 times, sorry, not 2 times 3, 3 times 3. So I'm looking for my pairs. So I've got 2 times 2, I've got 3 times 3, and so I know that this is going to be 2 times 2 times 3 times 3, which is 36. root 2. So it's 6 root 2, or maybe I go, okay, so square root would be 2, square root would be 3, 2 times 3 is 6, I'd be left with root 2. You know, there's lots of ways to do this. Feel what's comfortable. I like the method I showed you to begin with, which is the one that I'll just keep showing. So if I have 2 root 56, again, I'm not going to use the factoring tree. I'm just going to look for the highest perfect square that divides evenly into 56. So I'm going to use this chart I have over here. And I'm going to start with the perfect square that's closest to half. So I'm going to start with 25, which isn't going to work. So I'm going to try 16. So I'm going to go 56 divided by 16. Doesn't work. I mean, it goes in, but not evenly. So then I'm going to go 56 divided by, what's the next one? 9. And I'm going to go 56 divided by 4, and it worked. So 56 is 4 times 14. And notice again, this is 2 times root 56. So this is now 2 times the square root of 4 times the square root of 14. So when I take the square root of 4, it's now 2 times the square root of 14. And so 2 times 2 is 4 times the square root of 14. Okay, one more. Hey, pause the video, maybe give this one a go. You might be bored of listening to my voice by now. Okay, write my radicals. The highest perfect square that goes into 32, I can see right away is 16. So I'm going to go 16 times 2. So this is 3 times the square root of 16 is 4 times the square root of 2. So 3 times 4 is 12 times the square root of 2. Then we get into variables. And so when you're doing variables, you're going to look at your index. Now we're only simplifying square roots. When you look in your textbook, there are questions that simplify cubed roots. I've chosen not to cover those because it's not an articulated outcome. If you're curious, feel free to look, but we are only going to be simplifying square roots. So the process will always be looking for the exponent less than 3 that's divisible by 2, which I feel like is a really awkward sentence, but what you're going to do is that you're always going to have this x on the end, because x cannot take the square root of, because the index is a 1, or sorry, the exponent is a 1, and so x cubed is x squared times x. So x squared is an exponent divisible by 2, and I'd have an x left over. So the square root of x squared is x times the square root of x. All right, let's try another one. So what about y to the 7? So again, we're trying to find an exponent that's even so that I can take the square root of it, which means dividing the exponent by 2. And so if I have y to the 7, it would be y to the 6 times y. 6 is divisible by 2, the 1 is not. So I'm going to put y to the 6 in here, I'm going to put the y in here. Then I've got 6 divided by 2, so the square root of y to the 6 is y cubed times the square root of y. And then these last two questions are combining numbers and variables. So it's the same process. I draw my perfect square radical and then my leftovers, and I do them separately. So I'm looking at 27. What's the highest perfect square that divides evenly into 27? It's 9 with a leftover of 3. So again, 9 times 3 is 27. And then I'm looking for the highest even exponent less than 3. So that would be x squared, and so I'd be left with an x. And then I take the square root of the perfect square. So this would be 3x times the square root of 3x. You'll notice in the textbook, I think this textbook does it, sometimes they'll put like a little dash on the end to show you that that's the end of your square root sign. Just make sure that the radical sign goes all the way to the end of what's underneath of it. All right, pause the video, give this one a go. Hopefully you're coming back, or maybe you stayed with me. So I'm going to draw my two perfect squares. I'm looking at 72. Hopefully you're remembering from the first example that the highest perfect square that goes into 72 was 36 with a 2 left over. So 36 times 2 is 72. The highest even exponent that's less than a cubed is a squared with an a left over. And then 4 is divisible by 2. So I'm going to put that whole b to the 4 in the first bracket, and there's nothing needed for the second one. Then I take the square root of the perfect square. So square root of 36 is 6. Square root of a squared is a. Square root of b to the 4 is b squared times the square root of 2a. And that's it. So go practice simplifying radicals. It's a really, really important skill for further courses.